Hi there, my name is Zhongyang, and today I'm going to present our work predicting quality of video games experience using global scale telemetry data and federated learning. Okay, let's first look at the background. When playing a game, especially those with a fast tempo, like shooting game and action game, being too laggy is certainly a terrible experience. Frame rate, or frame per second, FPS is a key indicator to the game performance. It tells how many frames your gaming device can render every second on average. However, before buying a game, it's hard to accurately estimate the game performance on your own device, as the mainstream platforms only provide the minimum and recommended hardware requirements, and let the players to compare their own device's configuration with them. This is inconvenient and inaccurate, since not only the hardware affects the final performance outcome, operation system, game type, and optimization condition, as well as the game players' playing habits all cause impacts. Therefore, we plan to build a deep learning-based model to predict the FPS distribution based on all the factors mentioned just now. Here are some examples of how existing gaming platforms like Epic Game Store, Steam, and Xbox Games helps players decide whether their device can run a certain game. If we can provide more fine-grained prediction on game performance on a certain player's device, like a FPS distribution, then we can have a better estimation on how this game will perform on different scenarios. For example, many games include quite different things. Complicated things, which requires rendering a large number of objects, can have a lower FPS. On the contrary, simple things can lead to a way higher FPS. However, in order to predict the accurate FPS distribution, the model need to access both the hardware and software information, as well as some habitual hints from his or her device, which can make players hesitate. Therefore, we propose to further apply federated learning technique on this model. No data will be transferred to a server. Only the model update trained locally with local data will be transferred to and accumulated. This can guarantee the personal sensitive information secure. As for the exact game performance indicator, we applied the 95% FPS floor, or the low fifth FPS, as there is a previous paper has demonstrated that this indicator, compared to average FPS, can better represent how players perceive the laggy level of a game experience in a certain time period. 95% FPS floor is defined as follows. Assume the FPS is sampled every 5 seconds during a gaming session. After the sampling phase, sort these collected FPS samples, and then find the FPS value that is smaller than 95% samples. Some famous games like Black Myth Wukong, a AAA game released last year, have adopted this indicator in its pre-released game performance tester program. Our proposed game performance prediction model is beneficial to both the players, game developers, and game platforms. Players can be better informed about the estimated game performance and avoid buying games that cannot actually run well on their own devices. Game developers can also avoid massive negative comments caused by poor game performance. Game platforms can provide better service to gamers and therefore win more customers. In this work, we collected a huge gaming telemetry dataset from players all over the world, and this breakdown are shown in this page. In this dataset, players from the United States and Russia are the most numerous. As for our proposed model, input can be divided into two parts: quantifiable features and non-quantifiable features. The former includes player features like GPU and CPU configuration, and game features like game genre and release time. This feature can be directly collected and processed, then be fed into an encoder to generate an embedding. Non-quantifiable features include the player and gamer learnable kernels. Both kernels are randomly initialized tensors, and they evolve as the training process goes on. Each player is assigned a separate player learnable knowledge kernel, LKK, and each game is assigned a separate game LKK. When applied, they are concatenated with the embedding generated in the previous step and go through an additional merge layer to generate the residual compared to the previous embedding. In this way, no matter whether the LKKs are applied, the embedding are fit to the decoder are compatible, and the LKK only serve as a refinement information source. During the training, 4 different modes are applied and updated at the same time. These modes are: use no LKKs, use only game LKKs, use only player LKKs, and use both LKKs during the forward process. The results will be compared with the ground truth separately and generate four losses. The average loss of these four is treated as a final loss. For the training and updating strategy part, we adopted the federated learning as the overall framework. When a player finished some new game session, a local training process will be initiated. Each local training process accumulates some gradients calculated during the backpropagation process. This gradient are sent back to the server, and once accumulated gradients exceeded a certain threshold, central server will aggregate them and update the model using this gradient. Updated model will then be distributed to all local clients. This is the theory of the federated learning pipeline we used in this work. We tried to train using both centralized and federated learning method and found that the results are accurate and comparable with each other, showing the effectiveness of the federated learning mechanism. Also, one thing worth noting is that we divide the FPS range into 5 big chunks, which is 0 to 25 Hz, 25 to 45 Hz, 45 to 60 Hz, 60 to 155 Hz, and higher FPS. This is designed for the interpretability and use convenience. We also did some qualitative comparison between the predicted results and the ground truth, finding that in most cases our estimated 95% FPS floor distribution closely matched the ground truth. Even if there are some mismatches, the overall trends are still fine. For the convenience and easy of the interpretability for non-professional players, we mainly promote the 5-category FPS distribution prediction. However, we can provide more fine-grained 42 classes FPS prediction for more information. Professional players might find that useful to observe the concentration of the distribution, as more concentrated curves means that a more stable performance can be expected. From the result, we can find that the accuracy for the 42 classes prediction is also good. During the data processing, we also find some interesting insight in both micro and macro level. For example, we find that average 95% FPS floor among each country has a negative correlation with a Jinhe index, an important index that reflects the level of wealth inequity in a country. Large Jinhe index means larger wealth gap and more inequities, which can further result in more people cannot afford better gaming devices. Similarly, game performance shows a positive correlation with GDP per capita, and this relationship follows the logarithmic trend. For the micro-level insights, it's not surprising to see more powerful CPU and GPU result in better game performance. Also, desktop and server types of devices have a clear advantage compared to the tablets and notebooks. Thank you. That's all for this work.